my annotated thermo final exam. I'm going to be reading off my paper. For problem 1, state 1, we have two properties so we can fix the state. We have pressure and temperature. So we go to the saturated vapor liquid tables and I compared a constant pressure of 15 to the boiling temperature, and our temperature was less than the boiling temperature, which made me believe it was a liquid. From there, we used our temperature approximations to find the specific volume, internal energy, enthalpy, and entropy values. And then, so for state 2, we look down, it's a constant pressure process, so we know that it's going to have the same pressure, so we know one property, and we're given U. So for our pressure, we go over to the liquid vapor tables again, and we compare our U to their U, and we see that the U given is larger than the U for the vapor at that pressure. So then we know that it's a vapor, and then from there we can go to the vapor tables, find the corresponding U value to that pressure to find temperature, and then from there use the temperature to look up again the specific volume, enthalpy, and entropy. Process 2 to 3 is adiabatic, and we know this is a reversible process, so that means it's isentropic, so S2 equals S3. So that from there we know the entropy, we know one property, and we know the pressure, so we can fix the state. We look to the tables, and we find that S is larger than S gas for the vapor, which leads us to believe it's a vapor. And then we look at that corresponding S value matched with that pressure to find the temperature, and then from that temperature we look across to find the other values. Okay, and so for step 2, these are just changes in specific internal energy and enthalpy and entropy. So there's not that much interesting explanation going on because it's just delta U12, delta U23, and so forth. The only thing that's need explanation maybe is the isentropic state, and that is again just because the only reason that delta S is 0 and that S2 is equal to S3 is because it's reversible and adiabatic. So moving on to step 3, constant pressure process. So 1 to 2 is going to be the same pressure. It's expansion, so the volume is going to be increasing. And then again, it's an adiabatic expansion, so the volume will be increasing again, and an adiabatic expansion follows that pathway. For the TS diagram, it's kind of flip-flop. For constant pressure, it follows similarly to an adiabatic reversible process. And for a isentropic process, delta S equals 0, and we know that the temperature is going down, so that's why it's in that direction. For step 4, we can calculate the work 1 to 2 using the integral of PdV. Pull mass out, divide through by mass, and that leaves us with P and then the specific volumes with a little unit conversion from bar to kPa, and then the difference between state 1 and 2's specific volumes, we can find work 1, 2 over mass. Then for the first law for a closed system is as follows: delta U equals heat transfer minus work. So we divide through by mass, and then we get the rate of heat transfer as a function of, as a function of both work and internal energy, as shown. So we can find Q12 that way. For process 2 to 3, we know it's adiabatic, so heat transfer goes to 0. So then we're left with the first law, and it gives us the relationship between internal energy and work, as shown. For step 5, we are now in an open system, and 1 to 2 is a boiler, which is also a heat exchanger. And then from the textbook and your notes, we know that work per unit mass goes to 0 for heat exchanger and boilers. So it's just a function of enthalpy, and so H2 minus H1 gives us that value. And process 2 to 3 is an adiabatic turbine. Adiabatic implies heat flow, rate of heat flow is 0. So again, we are, in both these processes, we are neglecting kinetic and potential energy. So that gives us the equation that the rate of work per mass flow is equal to H2 minus H3, which we can solve for. So going to step 6, comparing an open system and a closed system for 1 to 2, discuss the reasons for the comparison. So 1 to 2 for an open system equals 0 because for an open system, we integrate VdP and pressure stays constant. So there's no change in pressure, so pressure is 0. So that's why that work term is 0. For a closed system, we integrate PdV and pressure stays constant. We integrate under the curve instead of sideways. And as a result, we get an actual value for that. Now to step 7. For step 7, we are looking at a process, an adiabatic expansion through a gas turbine. Similar to step 5, we know that Q dot drops out of the term, and so it asks if kinetic energy is important when calculating. So I calculated with taking kinetic energy into consideration and then neglecting kinetic energy. And what we found was that the results varied when you included kinetic energy. So that would determine that kinetic energy is important. Moving on. Problem 2a, are adiabatic and isothermal processes the same? No. Adiabatic means there's no heat transfer, but work done in the system can still change the other properties of the system, which temperature is a property. Isothermal refers to temperature being constant, but work and heat can still change because input of work can change the heat transfer term, and that would go against the definition of adiabatic. If you hold open the door to hold it to the refrigerator, will the temp increase? The temperature will increase because you are inputting work, and now there is no longer, when the refrigerator was closed, you have a cold reservoir, which is inside, and you have a hot reservoir, which is the kitchen. The refrigerator is in the kitchen. But when you open the door, you no longer have the cold reservoir and hot reservoir being different things. So the thermal energy that's being taken out of the cold reservoir by the input of heat is actually rejecting the heat just into the room itself. So you're not going to actually cool down anything. Between the same pressures, does it take more to compress a flow of liquid water or to compress a flow of liquid vapor? Compressing a flow of vapor water takes more work than compressing a flow of liquid water. Vapor water has a higher specific volume than liquid water, and according to workflow equation, m dot times p times specific volume is what workflow is equal to. And because workflow is proportional to specific volume, having pressures be constant, we know that the substance with the higher specific volume will have more work to compress the liquid, which is compress the liquid or the vapor. So the vapor would require more workflow to compress it. The change in entropy between two states is term to be the. So this is essentially asking what is the difference between delta S reversible or delta S irreversible. And for a reversible process, the entropy production is 0. And for an irreversible process, the entropy production is greater than 0. So by that fact, the entropy equation has an entropy production term in it, the second law. So the one with it equaling 0, the reversible process, will be a lower entropy than the one that has an entropy production, which is irreversible. Can you reduce the entropy of a system? Yes, you can reduce the entropy of a system, either through heat transfer out of the boundary or mass leaving the system, because mass contains entropy. And if more mass leaves the system containing entropy or heat transfer, then the entropy of the system can decrease. So the diagram of a heat pump cycle, please describe entropy. So TC from the cold thermal reservoir to the cycle, you are losing Q, so you are losing entropy, and then you are injecting heat transfer into the hot reservoir with the addition of a work, and so QH is equal to the work cycle plus QC. So by that logic, the work entering the cycle is going to increase the entropy of our system, making it greater. Please fill in the blank. So delta S of an irreversible cycle is greater than delta S of a reversible cycle because of the entropy production. Going on to problem 3. For problem 3, we sketched this on a PV diagram. 1 to 2 is adiabatic compression, so we know that the volume is getting smaller, and it goes that. Constant pressure, expansion, and the volume's increasing. Adiabatic expansion, again increasing, but down to the right, and then again constant pressure, compression back. For an open system that is adiabatic and reversible, which means it's isentropic, we use the variable specific heats. We know T1, we know P2 and P1, so we can solve for the entropy at state 2 for temperature 2. And so once we solve for that, we can look up the corresponding entropy value for that and then find that respective temperature, or what I just did was I found the respective enthalpy. And this was interpolated. So from there, we know it's a reversible process. So H2 is equal to the isentropic H2S. And then so the Q term drops out of the second law, and kinetic and potential energy can be neglected. So we get that work is a function of H1 minus H2S. So we get a value. Heat transfer is 0 because it's adiabatic. For process 2 to 3, constant pressure, we know that work drops out because work is the integral of V dP, and P is the same at state 2 and 3. Again, potential and kinetic drop out. So we know H2 because we just calculated it. We can look up H3 because we are given T3, and from T3 we go to the tables, we find H3, and we can calculate H3 from there. Again, work is 0. From process 3 to 4, it's the exact same methodology as 1 to 2, and I'm running long on time, so I've explained how I did 1 to 2, and that same process applies to 3 and 4. Process 4 to 1 is the exact same thing as process 2 to 3. It is constant pressure, so work drops out, and Q is a function of enthalpies, or it's an expression of enthalpies, okay? So for step 4, using heat transfer cycle, determine determine thermal efficiency. So thermal efficiency is the total work of the cycle divided by the Q from the hot reservoir. So the Q from the hot reservoir is from process 2 to 3, because that is for the definition of a power cycle. So we sum up all the works and divide it by process Q to 3, and we get a value of 0.368 or 36.8%. Going to step 5, determine the thermal efficiency using 1 minus Tc over Th. So we know that Qc over Qh is equal to Tc over Th. We know Qc and we know QH by the definition of a power cycle, of where heat is being dumped and injected into. So we can solve for the equivalent expression of Tc over Th, and then it's the thermal efficiency is 1 minus that, and then we get the exact same value as we got for the previous step. And comparing this, it makes sense because the max efficiency is the reversible efficiency. What is the mass flow rate of air if the cycle produces a net power of 10 megawatts? So the net cycle is equal to 10 megawatts, and so we set each of the individual, we add up each of the individual work terms and multiply through by mass flow, and then divide by mass flow to get an expression relating the work 1 to 2 and work 3 to 4 over the total net output. So we get a value for mass flow. The last problem. Using our answer for step 6, what's the volumetric flow rate? So we can calculate specific volume using the ideal gas law, and we already know mass flow. A times V is what gives us volumetric flow rate, and that is it.